Okay, last time we discussed the two fundamental theorem of calculus, right? The first fundamental theorem of calculus tells us that if the function g of x is given as the integration of another function f of t dt from 0 until this x, where this x is the argument of this function g, then derivative of the g is equal to the f of x. Okay, so let's do an example. Example is like this. So let's say g of x is the integration from 0 to the x of the sine of t dt. Okay? If you give one x, one value for the x, it should give you like the answer. Okay? So what is the g of, for example, pi? So in order to find this, we need to integrate this function, sine of t, from 0 until the pi, right? So the integration of this, it will be antiderivative, which is minus cosine of t, right? Then I need to put the values from 0 to the pi. So if I put the pi, it will be minus 1, so which is 1, right? If I put the 0, it will be 0, it will be plus 1, right? So the answer is 2. So when the g gets the value pi, it gives you back the 2, okay? Or is it 2? So this is minus cosine of pi plus cosine of 0, right? Which is minus minus 1 plus 1, which is 2. Okay? So it just tells us that if you have this function g of x, and if you need to take the derivative of this g, derivative of the g will be simply sine. Okay, this is what does the fundamental theorem of calculus 1 tells you. So we're going to check this in differently. So what we'll do is we will first of all integrate this first, and then we'll take the derivative. Okay, and we'll check whether this is sine of x or not indeed. Okay, so if you integrate this, what you will get? So the minus cosine of t, then we need to put from 0 to the x, right? So if you put the x, it will be minus cosine of x. If you put the 0, it will be 1, so plus 1, right? So g of x is actually equal to the minus cosine of x plus 1, okay? You can write this either like this, okay? So if I say, hey, what is the derivative of the g? It will be equal to the sine of x, okay? Do you see this? So how did you get the sine of x? By taking the derivative from this function, right? But you could tell me this answer without taking the integration and taking the derivative, right? So if I say, hey, the function, another function, g of x is given as the integration from 0 to the x, e power of sine of x squared plus 3 in the power of e in the power of x cubed, or let's make it t here, so in order to differentiate the variables. Okay, if our function is given g of x is equal to the integration from 0 to the x e in the power of sine of t squared plus 3 e in the power of t cubed dt, and if I say, hey, what is the derivative of the g with respect to the x? You don't need to integrate this, then take the derivative. You can simply tell me, hey, this will be equal to the e in the power of sine of x squared plus 3 e in the power of x cubed. Okay? Derivative of this function will be the same as this one. The idea is like this. The idea is we say the derivative and the integration are, or antiderivatives, are reverse operations. Okay? So if derivative does something, antiderivative undoes the same thing. Okay? Derivative is doing something, antiderivative is undoing the same thing. Okay? They are reverse operations. Okay? So that is why if you're integrating this sum function and then taking the derivative, they will cancel each other. Okay? But they cancel each other only in the case if the x is here on the borders of the integration. Okay? If the x is inside the integration, this is the different story. Okay? Because if the x is inside the integration, after the integration, you will get the value, the number. Okay? So the second fundamental theorem of calculus is called the Newton-Leibniz formula. So it tells us that, hey, if you would like to find, evaluate the definite integral of f of x dx from a to the b, then this is equal to antiderivative of this function at the point b minus antiderivative of this function at the point a. Okay? For example, if I ask you to calculate the integration of the x in the power of 4 dx from minus 1 to the 2, then you first of all need to find the antiderivative of the x4, right? Which is x in the power of 5 divided to the 5. Then you have to evaluate this at the point minus 1 and 2 and subtract them. Okay? So minus 1 and 2 and subtract them. So 2 will be 32 over 5. Minus 1, it will be plus 1 over 5. The answer is 33 over 5. Okay? So today we will talk about the substitution rule. So sometimes it is necessary for us to integrate the functions like this when figuring out the antiderivative is difficult. Okay? So we don't know what is the antiderivative because in our standard table there is no such a function. Okay? So in these cases we have to use the substitution. Okay? So we say that we would like to introduce the substitution like u will be equal to the 1 plus x squared. Okay? Then I will find the derivative from the both sides with different variables. With respect to the u from the left-hand side, with respect to the x from the right-hand side. Okay? So what is the derivative of the u from the right-hand side? Is 1. Right? What is the derivative of the 1 plus x squared with respect to the x? Is 2x. Right? Then additionally, we have to multiply du because it shows that, hey, we just took the derivative with respect to the u, right? And here we need to multiply this with the dx because it shows us we just took the derivative with respect to the x, okay? Because if I say, hey, here is a tx, this is the derivative of some function, okay? So tell me, what is the antiderivative? It depends, right? If I write, for example, here dx, you will tell me, hey, the antiderivative is equal to the x squared, okay? So if you're given tx dy, for example, the antiderivative will be equal to the txy, right? Because you will consider tx just the constant, right? So what is the derivative of the txy with respect to the y? Is tx, right? So the derivative of the txy with respect to the y is tx, okay? So that is why it is important to show this dx or dy, right? If you're given tx, the antiderivative might be different depending on what is the variable which you take the derivative, okay? If you take the derivative with respect to the x, then the antiderivative will be x squared. If you take the derivative with respect to the y, the antiderivative will be 2xy. Okay? You understand this? So that is why it is important to put this there. So now the idea of the substitution is like this. So if you decide to substitute your x with another u, you have to substitute every single x under your integration, every single, okay? So it is impossible when you substitute like half of the x's and you will leave half of the u, like x's without substitution, okay? So you have to substitute all the x's with the u. So here, I have to do the substitution. I know that the 1 plus x squared can be written as the square root of u, right? And what is left here in our integration? Tx multiplied to the dx, which is exactly du, right? So multiply to the du, so which can be integrated using the rule, right? We know that the u can be written, square root of u can be written as the in the power of 1 over 2, right? Du, then according to the rule, it will be u in the power of 1 over 2 plus 1 divided to the 1 over 2 plus 1. So the answer will be 2 over 3 u in the power of 3 over 2, okay? So if it is necessary, you can resubstitute back the x, okay? So the answer will be with the x, 2 over 3 1 plus x squared in the cube from the square root. Okay? So in general, the idea is like this. So if your function under the integration is given in this form, where you're given some function which depends on another function, multiplied to the derivative of this function g, then you can make the substitution. So what kind of substitution we need to make here? So we are going to make the substitution. U will be equal to g of u, and du will be equal to the g prime of x multiplied to the dx. Right? Derivative of the left-hand side is equal to the 1, and we have to multiply this to the du. Derivative of the right-hand side part is g prime of x, and we have to multiply this to the dx. Do you understand why we have to multiply this? Right? It is important because we have to know what is the variable which you took the derivative. Okay? Then this integration simplifies in the form f of u multiplied to the du. Okay? So let's do a couple of examples. So let's start with examples. So integration of x cubed cosine of x4 plus 2 dx. So whenever you would like to use the substitution, you need to see the structure. You need to see, hey, there is a function which I can substitute with the u, and the u prime is also there. Okay? Derivative of the u is also there under your integration. So what do you see from here is you can substitute u as x4 plus 2 because there is a derivative of the x4 plus 2 as well, right? What is the derivative of the x4 plus 2? It's 4x cubed, right? X cubed is here, right? You can deal with some constants. If the derivative of your substitution differentiate was from this function x cubed only to the constant, you can do something. Okay? Yes? So if it differs not by the constant, but by the variables, for example, by the x4. If it would be, for example, x4 here, then it will be really difficult to use the substitution here. Okay? So du will be, what is the derivative of this? 4x cubed, and you have to multiply this to the dx because you took the derivative with respect to the x, right? Because if you take the derivative from the 4x in the power of 4 plus 2 with respect to the y, for example, this might be 0, right? Okay, so it is important. Now we have to use the we have to do the substitution, and let me rewrite the function under the integration as the two parts: cosine of x4 plus 2, okay, multiplied to 4x cubed dx, okay, and I have to multiply this integration to the 1 over 4, okay, to be the same with this one, right? The reason why I multiply this to the 4, because I would like to substitute the whole, this blue thing, with the du, right? So you see, so this is exactly equal to the du, right? And I can make this by multiplying this to the 4, but since I multiply this to the 4, I have to divide this to the 4 as well, okay? So the answer will be integration 1 over 4 of the integration cosine of u multiplied to the du, right? After the integration, this will be equal to the 1 over 4 sine of u plus some constant, okay? If you want, you can resubstitute this back. So let's do a couple of examples. Example of the integration of the tangent of x. So previously, we talked about the derivative of the tangent, right? What is the derivative of the tangent? So you did this in one of the exams in the class. Do you remember? Right? Derivative of the tangent will be equal to the 1 over cosine square of x. We can get this, for example, using the quotient rule, right? So now I'm asking you, what is the integration of the tangent of x? So let me rewrite this as the sine of x divided to the cosine of x. The first thing which you need to do is, you need to be able to see the substitution, some variable which you have to introduce, okay, and its derivative. Do you see this? So I see this, right? So this is sine and cosine. So if you substitute one of them, its derivative is also there, right? But the thing is, like, its derivative should be there, like this, right? So it should come together with a dx, right? So that is why we can substitute here the cosine. Okay? If you substitute the sine, then you cannot substitute the u as well. Okay? So u will be equal to the cosine, and what is the du? Derivative of the cosine, which is minus sine of x multiplied to the dx. Okay? Now let me rewrite the integration again differently. So sine of x dx was the minus divided to the cosine of x. And I have to multiply this integration to the additional minus, right? Because I multiplied here the numerator to the minus, right? Now the integration becomes exactly like this is equal exactly to the du, right? And the denominator is exactly as the u, so which is equal to the minus ln of u, okay? Or minus ln of cosine. Minus ln of cosine x plus c. So the integration of the cotangent can be found analogously. Now let's try to integrate this function. So integration of the square root of 1 plus x squared multiplied to the x in the power of 5 dx. So what kind of substitution do you see here? Okay, so we can make the substitution u will be equal to the 1 plus x squared, right? But the thing is, its derivative should be also there, right? So what is the derivative of the left-hand side? Is 1, right? Then we have to multiply this to the du. What is the derivative of the right-hand side part? Is tx, right? Then we have to multiply this to the dx, right? Do you see tx, dx here? Yeah, there is x dx, right? So we can write the integration like this. So let me write. So square root of 1 plus x squared, right? Multiplied to x in the power of 4, multiplied to the tx dx. Okay? Can I write this integration as this one? No, right? Because here is additional 2 here, right? I have to multiply this to the 1 over 2, right? Now I can do this, right? So this integral is the same as this one, right? The red one is the same as the black one, right? Now we need to think, is it possible to substitute everything under this integration with the u? Okay? So is it possible to substitute the first part, this one? If you substitute it with the u, what you will get? Just the square root of u, right? Is it possible to substitute this part? Yes, so this will be just this du, right? Is it possible to substitute the x in the power of 4? Yes, right? So what we can do is we can find the x squared from here, right? So x squared from here will be equal to u minus 1, right? And what will be the x in the power of 4? It will be u in the minus 1 in the square, right? So it appears I can substitute x in the power of 4 with the u as well. It will be written u minus 1 in the square. Okay? Now everything is substituted with the u. So square root of u multiplied to the u minus 1 in the square du. Okay? So the point of the substitution is that it should be easier for us to do the integration. Okay? So now it is easier because everything is a polynomial, right? So the only thing which you have to do is you need to open up all the brackets. So 1 over 2 integration of the square root of u multiplied to the u squared minus 2u plus 1 du, right? Then we multiply everything with the square root of u, so this will be equal to the 1 over 2 u squared multiplied to the u from the square root. Basically 2 plus half, right? Because the power of this is u in the power of 0.5, right? 1 over 2, right? So if you multiply them, you need to add their powers, right? So this will be u in the power of 2.5, right? Minus 2 u in the power of 1.5 plus u in the power of 0.5 du. Okay? Now we need to integrate every term separately. So this will be 1 over 2. What is the antiderivative of the u? 2.5. So this is u 2.5 plus 1 divided to the 2.5, right? Plus, or sorry, minus u 1.5 plus 1 divided to the 1.5 plus 1 plus 2 u 1.5 divided to the 1.5. Okay, this is the answer, plus the constant. Do you see? The idea is to substitute every single u with the variables.